We're going to talk about hypothesis testing for the difference between two independent means. Okay, so we're going to go over the goal of hypothesis testing in general. We've only looked at it for one mean so far, but we're going to look at how it changes just very subtly when we talk about two means. And then we're going to re-talk about the sampling distribution of the difference between two means. If you had just watched the confidence interval for two means, then you don't need to watch this one. Then you don't need to watch that section. Then we're going to talk about the same conditions for doing hypothesis testing as for confidence interval. They need to meet three conditions before you could do either of these two. Then we're going to talk about the modified steps of hypothesis testing for two means and the formulas that go with those steps. Okay. So let's talk about the goal of hypothesis testing. In one sample, what we wanted to do was reject the null if we got a sample that was significantly different from the hypothesized mu. For instance, significantly lower or significantly higher, right? And remember, significant doesn't mean important like it does in our modern use of the word. It actually means does it stand out? Is it weird enough, right? Does it stand out from the hypothesized mu? And in those cases, we reject the null. And really, our goal is to reject the null. We can only say whether something is sufficiently weird. We can't say whether it's sufficiently similar, right? And so an experiment is actually a success if they reject the null. If they don't reject the null, it's considered a null experiment, or what we think of as uninformative, which is not actually true, but that's sort of how it traditionally is thought of. Okay. But remember, this is in the case where we only have one sample and we have a hypothesized population. Here, we have two samples, right? And in order to reject the null, we need to get samples that are significantly different from each other, right? So they stand out from each other. So X is different from Y, Y is different from X, right? That's what we're really looking for. Once again, just like the one sample, we can't say whether they're sufficiently similar, but we can say whether they're sufficiently different. And it's okay if X is significantly lower than Y or X is significantly higher than Y. We don't really care. We just care about significantly different. And this, if you don't care about which direction, these are called two-tailed hypotheses. Now let's think. If X and Y are really different from each other, then X minus Y should not be 0. But if X and Y are exactly the same, X equals Y, then X minus Y will be 0, right? Because you could think of this almost as X minus X, right? Because X equals Y, right? And so, and if you want to think about it algebraically even, if you add Y to each side, you would get perfectly X equals Y, right? So if X and Y were the same, we should expect their difference to be 0. Makes sense, right? Makes sense. Okay. So now let's just review very briefly the sampling distribution of the difference between two means. This is the case where we don't know what the population is like. But because of the central limit theorem, we actually end up knowing quite a bit about the S-DOMs. Oh, so for this is X, the population of X, and this population of Y. So this is the S-DOM of X bar, so it's a whole bunch of X bars. And this is the S-DOM for Y, which is a whole bunch of Y bars, right? And so we know some things about these guys. And we also know we could figure out the standard error from the sample. Right? So what's nice about this is we don't need to know anything about the population. All we have to do is know the standard deviation of the sample, which we could easily calculate in order to figure out, in order to estimate the standard error of these two populations. Great, right? And once we have that, now we could start talking about the S dot, the sampling distribution of the difference between means. Right? And here, what we really want to do is instead of finding mu sub x or mu sub y, we want to know mu sub x bar minus y bar, right? And so here you have to think of pulling out one sample from here, one sample from here, getting the difference, and then plotting it, right? If these guys are normal, we can assume this one to be normal. And not only that, but we could figure out the standard error of this guy as well, just from knowing these. Because the standard error, the standard error is going to be the square root of s sub x squared, so the variance of x over n sub x, plus the variance of y over n sub y. And these are all things that we have, right? We don't need anything special. We don't need sigma or anything like that. We just need samples in order to calculate this. If these two distributions, or actually if these two distributions, the population distributions, if we have a reason to suspect that these have homogeneous variance, if their variances are the same, then instead of s sub x squared and s sub y squared, we could actually use s pooled squared, right? But we won't be doing that for this example in this lesson, but you can. Okay, so remember, the rules of the S dot are very similar to the CLT. If the S dom for x is normal and the S dom for y is normal, then S dot is normal too. There's two ways that this could be true. The first way is if populations are normal, right? If population of x and population of y are normal, then we could assume S dom for x and S dom for y are normal. Or your other possibility is if n is large enough. Okay, then we want to talk about the mean for the null hypothesis. The null hypothesis, remember, is saying that the population of x and the population of y, the difference between them is going to be 0 because they're similar, right? And so the null hypothesis is saying those two are similar, which means that the means of the sampling distribution of the means, right? The S DOM's means, those are going to be similar, which means that when we subtract them, it's going to give us 0. So the null hypothesis says the mean of these differences of means is going to be 0, right? That's the null hypothesis. And that's really saying that the S DOM for the x and the S DOM for the y are very, very similar. That's all it's saying. Okay, now let's talk about standard error for independent samples. Remember, we're still talking just about independent samples. When variance is homogeneous, that's when we use that S pooled idea, right? And so that will mean that S sub x bar minus y bar is going to be equal to, and pretend that you're writing out just the regular idea where you're dividing by n sub x and n sub y. But instead of using the variance from x and the variance from y, we're going to use that pooled variance idea. So that's going to be S pooled, the variance pooled, and here also variance pooled. Now some people think, oh, why don't we just put that on top and put n sub x plus n sub y at the bottom? Well, that would be algebraically wrong because, remember, these are the denominators, right? We would have to have common denominators in order for us to put these together, and we don't have common denominators yet. Okay, so what about in the case where variance is not homogeneous? And this is the vast majority of time. And when in doubt, when you don't know anything about the variance of the populations, go with this one. It's just a safer option. So that's going to mean that this standard error is represented by the variance of x over n plus the variance of y over n. Add these together and square root the whole thing. Okay. So just to recap, same conditions must be met in order to do hypothesis testing for two means as the conditions for doing a confidence interval for two means. So it's that the two samples were randomly and independently selected from two different populations. It's reasonable to assume that both populations that the samples come from are normally distributed, or the sample sizes are sufficiently large. This is to ensure the normality of the SDOMs. Also, in the case of sample surveys, the population size should be at least 10 times larger than the sample size for each sample. And this is just to assume, so that we could assume replacement, right? Because probability axioms change when you don't assume replacement. Okay. Now let's go on to the steps of the hypothesis testing. These are the same steps as you did when you had one mean, except now that we're subtly changing just a few things. And I'm going to highlight those changes as we go through this. So first we need to state our hypotheses. And remember, now instead of having just a hypothesis that the mean of the population equals this, what we're really saying is that the mean of x, of the population of x, and the mean of the population of y, those are the same. So mu sub x minus y will be 0, right? You could also write it as mu sub x equals mu sub y, right? Either way. And the alternative is that they're different from each other in some way. Then we pick a significance level. How different do these two populations have to be for us to say they're different? Then we set a decision stage. But instead of drawing the SDOM, now we draw the SDOD, right? Because now we're looking at the differences between these two means. We identify critical limits and rejection regions. We also find the critical test statistic, the boundaries, right? And in order to do this, we have to find the degrees of freedom for the difference, right? We can't just use the degrees of freedom for one, degrees of freedom for the other. We have to actually add them together. And then use the samples and the SDOD to compute the mean difference. So now we're not just computing mean, but we're computing mean difference. Mean difference is test statistic as well as the p-value. And then we compare the sample to the population, the hypothesized population. And we either reject the null or not, right? We reject the null if our test statistic and p-value lie outside that, lie in those zones of rejection, where it's like, these are the weirdo zones. Like, this is when we know, man, our sample is really different from this population. Okay, now let's talk about the different formulas that go along with these steps. So remember, the first step is going to be what is the hypothesis, the null hypotheses as well as the alternative, right? And so this isn't really a formula, but it's helpful to remember that this is what we really mean, right? Versus mu sub x bar minus y bar does not equal 0. So this is often what's going to be the case. Now you could rewrite this as mu sub x bar minus mu sub y bar sometimes, but that will be in the case where that will also be, there are some mathematical ideas that you have to learn before you could write that. So why don't we leave that aside for now. Okay, second thing is significance level. So here there are no formulas really, but you should know that when we say alpha equals 0.05, we're talking about that false alarm rate. This is the rate of rejecting the null when the null is actually true. So this is a very low rate of false alarms. And when we say alpha equals 0.05, it's not that we calculated it, but it's just that by convention, science tends to say this is a reasonable level of significance. Sometimes people are more conservative and they want 0.01 or 0.001. Number 3, we need to set that decision stage. And it's helpful to draw the S-DOD, right? And it's helpful to have our hypothesized population here. So mu sub x bar minus y bar, right, equals 0. So we assume that this point is 0. One thing you'll probably also want to know about the S-DOD is the formula for standard error, right? So the formula for standard error of the S-DOD, we've written this a lot of times now, right, is the variance of x over n sub x plus the variance of y over n sub y, right? And another thing you probably want to know is that we need to find these critical t. So we need to find the t values here, right? And in order to find that, you'll need to know the degrees of freedom for the difference. And that's pretty easy. It's the degrees of freedom for x plus the degrees of freedom for y, right? And to find this, it's n sub x minus 1. To find that, it's n sub y minus 1, right? So we could write this as n sub x minus 1 plus n sub y minus 1, right? So you could write it like that. And then I think that's all you need to know for the decision stage. Okay. And so step 4 is you have to compute the mean difference, the sample's mean difference. So sample's mean difference, right? You need to calculate its test statistic as well as its p-value. So remember, we're going to be using t from here on out because obviously we're using s instead of sigma. And so let's talk about how to come to the sample t. Let me write this as sample t. Well, the sample t is really the distance between where our sample difference is versus this hypothesized difference, right? But we don't want it just in terms of that raw distance. We want it in terms of the standard error, right? So it's really going to be whatever our x bar minus y bar is. This is our actual sample difference minus 0, right? Because that's our hypothesized population divided by this standard error, s sub x bar minus y bar, right? And that will give you how many standard errors away are actual mean differences from 0. And once you have this t value, then you could find, and you have the degrees of freedom, then you could find the p value, and then you could reject or accept the null hypothesis. Reject or do not reject. That's really the technical idea there.